Introduction to Azure Virtual WAN. Welcome to the channel. Please consider subscribing. I produce videos daily covering a wide variety of cloud topics with focus on networking. Also, hit the bell icon to get notified of new videos. Today we're exploring Azure Virtual WAN, Microsoft's revolutionary approach to enterprise cloud networking. As you can see from the diagram on this slide, Virtual WAN addresses the major challenges organizations face with traditional networking approaches. Where traditional networks require complex routing tables, manual failover procedures, multiple point solutions, and have limited global reach with high management overhead, Virtual WAN provides elegant solutions to each of these challenges. Looking at the metrics displayed, you can see Virtual WAN delivers deployment times that are 75% faster than traditional approaches. This isn't just marketing speak. I've personally seen deployments that would have taken months with traditional networking completed in days with Virtual WAN. The 50% cost reduction compared to MPLS networks is achieved through intelligent use of internet connectivity combined with Microsoft's backbone, eliminating expensive dedicated circuits. And with over 60 Azure regions globally, you have unprecedented reach for your network infrastructure. The 5 revolutionary features listed in the highlight box are what truly set Virtual WAN apart. First, it's a software-defined global network, meaning you can programmatically control and adapt your infrastructure. Second, it leverages Microsoft's backbone, one of the world's largest private networks, ensuring your traffic travels on optimized paths. Third, unified management gives you a single pane of glass for global connectivity instead of juggling multiple tools and interfaces. Fourth, intelligent routing with automatic path optimization and failover means the network self-heals and self-optimizes. Finally, integrated security with native firewall and threat protection means security isn't bolted on as an afterthought but built into the fabric of your network. What we're seeing here is a fundamental shift in how enterprise networks are built and operated. Instead of managing individual components and connections, you're managing intent and policy while Azure handles the implementation details. This transformation enables IT teams to focus on business outcomes rather than network plumbing. Understanding Virtual WAN architecture. Let's dive into the Virtual WAN architecture shown on this slide. The first thing to understand is the Azure CLI command displayed at the top. The AZ Network vWAN create command is how you instantiate your Virtual WAN resource. Notice the type parameter is set to standard. This is crucial. Never use basic for production as it lacks essential features like branch-to-branch transit and express route support. The allow branch-to-branch traffic and allow VNet to VNet traffic parameters set to true enable any-to-any connectivity, which is one of Virtual WAN's key benefits. The diagram illustrates the separation between the control plane and data plane, which is fundamental to understanding Virtual WAN's architecture. The control plane, shown on the left, consists of the Virtual WAN resource itself, which connects to the resource provider and configuration manager. This is where all your policies and configurations are stored and managed globally. The data plane on the right shows the actual hubs. In this example, Hub East US, Hub Europe, and Hub Asia. Notice the dotted lines between the hubs? These represent the automatic full mesh connectivity over Microsoft's backbone that Virtual WAN creates without any manual configuration. Looking at the architectural principles table, you can see how responsibilities are divided. The Virtual WAN resource is global in scope and managed by you, the customer. It serves as the policy and configuration container for your entire network. Virtual hubs are regional in scope, but crucially, they're managed by Microsoft. This means Microsoft handles all the complex routing, high availability, and infrastructure management within each hub. Gateways are hub local and also Microsoft manage, serving as your ingress/egress points for different connection types. Route tables are hub local with hybrid management. You define the policies, but Microsoft implements the routing. The key insight from this architecture is that you are defining what you want, the intent, through the Virtual WAN resource, and Microsoft's infrastructure automatically implements how to achieve it across all your hubs. This separation of concerns dramatically simplifies network management while providing capabilities that would be extremely complex to implement yourself. When you create a virtual WAN with the command shown, you are not just creating another Azure resource. You are instantiating a global network control plane that will orchestrate connectivity across your entire organization. The properties shown in the comments, such as allow branch-to-branch traffic, allow VNet to VNet traffic, and Office 365 local breakout category, are examples of the global policies you can set that automatically apply across all hubs in your virtual WAN. Core Components Deep Dive. This slide breaks down the core components that make up your virtual WAN infrastructure. Let's start with the virtual hub creation shown in the left code block. The AZ Network vHub Create command deploys a managed virtual network that serves as the regional connectivity point. The address prefix parameter of 10.0.0.0/23 allocates IP space for the hub's infrastructure. This /23 network is carved up automatically by Azure into subnets for different purposes. A /27 for the route server subnet, a /26 for the gateway subnet, and if you are using a secured hub, another /26 for the Azure firewall subnet. On the right, we see VPN gateway creation with scale units. This is where you define your connectivity capacity. Each scale unit provides 500 megabits per second of throughput and supports 1,000 tunnels. In this example, with 4 scale units, you get 2 gigabits per second aggregate throughput and support for up to 4,000 concurrent tunnels. The Generation 2 parameter is important. It allows scaling up to 20 gigabits per second if needed in the future, while Generation 1 tops out at 10 gigabits per second. The diagram in the middle visualizes the virtual hub's internal architecture. You can see how the hub's address space is subdivided and how multiple gateway instances are deployed for high availability. Notice there are 2 VPN gateway instances and 2 Express Route gateway instances. This active-active configuration is automatic and provides redundancy without any additional configuration on your part. The component sizing guide table at the bottom is particularly valuable for planning. For VPN scale units, a small deployment might use 1 to 2 units for 500 to 1000 megabits per second, while an extra-large deployment could scale to 20 units for 10 gigabits per second. For Express Route, the SKUs range from ERGW1AZ at 1 gigabits per second to ERGW3AZ at 10 gigabits per second, with the option to add fast path for ultra-low latency scenarios. Hub address space recommendations range from a /24 for small deployments to a /22 for large ones. What is important to understand is that these are not just arbitrary numbers, they represent real architectural decisions. Choosing 4 volts PN scale units is not just about bandwidth, it is about having enough capacity to handle your peak loads while maintaining performance. The hub address space needs to be large enough to accommodate all the managed infrastructure plus any future services Microsoft might add. These components work together to create a robust, scalable foundation for your global network. Planning your virtual WAN deployment. The planning process shown in this slide's flow diagram is critical to virtual WAN success. Starting with requirements analysis, flowing through regional design, IP planning, capacity sizing, migration strategy, and finally validation. Each step builds on the previous one. This isn't just a theoretical exercise. Following this process prevents costly mistakes and rework later. The Regional Hub Placement Strategy section contains crucial decision-making criteria. Notice the latency requirements. Same region delivers sub-2 milliseconds latency, adjacent regions 10 to 30 milliseconds, and cross-continental 100 to 250 milliseconds. These aren't just numbers to memorize. They directly impact your hub placement decisions. The example shows a real trade-off many organizations face. Deploying a single hub in West Europe covers all of the EU with less than 30 milliseconds latency for $182.50 per month, while adding a second hub in North Europe reduces latency by 10 to 15 milliseconds but doubles your hub costs to $365 per month. This is where you need to understand your application requirements. Is that 10 to 15 milliseconds reduction worth the extra cost? The IP address planning template table demonstrates proper address space allocation. Notice how each component has a specific allocation. Hubs use /23 networks, 10.0.0.0/23, 10.0.2.0/23. Production VNets get a full /16, 10.10.0.0/16, and branch networks another /16, 10.100.0.0/16. The growth factor column is critical. While hub address space is fixed, you need to plan for 50% yearly growth in production VNets and 20% growth in branch networks. The P2S pool at 172.16.0.0/16 has a 100% surge factor, acknowledging that remote user counts can double during emergencies. The capacity planning calculations shown in the code block walk through a real-world example. With 150 sites averaging 20 megabits per second but peaking at 50 megabits per second, the aggregate peak bandwidth is 7,500 megabits per second. Dividing by 500 megabits per second per scale unit gives 15 units, but adding 20% headroom brings us to 18 units. Deploying across 2 hubs means 9 units per hub. This mathematical approach ensures you have adequate capacity without over-provisioning. For ExpressRoute sizing, the example shows a common pattern. Primary and backup 1 gigabits per second circuits connecting to an ERGW2AZ gateway that provides 2 gigabits per second capacity. This ensures the gateway can handle the full bandwidth of both circuits if needed, providing true redundancy rather than just failover capability. Step-by-step deployment guide. This slide presents a complete deployment script that you can use as a template for your own virtual WAN deployments. Let's walk through each section to understand not just what the commands do, but why they are structured this way. The script starts with proper error handling using sed-e, which causes the script to exit if any command fails. This is crucial for deployment scripts. You do not want to continue if a critical step fails. The logging function timestamps every operation, creating an audit trail that is invaluable for troubleshooting or compliance purposes. Step 1 creates the resource group with proper tags. Notice the tags include environment equals production, managed by network team. These are not optional decorations. Tags are essential for cost management, access control, and operational procedures. Many organizations have policies that require specific tags on all resources. Step 2 creates the virtual WAN itself. The script captures the resource ID in a variable VWAN ID for use in subsequent commands. The parameters allow branch-to-branch traffic and allow VNet-to-VNet traffic are both set to true, enabling full any-to-any connectivity. This is almost always what you want in production deployments. Steps 3 and 4 demonstrate a crucial optimization, creating both hubs in parallel. Notice the ensign at the end of each hub creation command and the process ID capture. Since each hub takes 30 to 45 minutes to deploy, running them in parallel saves significant time. The script then uses the wait command to ensure both complete before proceeding. Step 6 deploys the VPN gateway with 4 scale units and Generation 2 specification. This provides 2 gigabits per second of capacity with room to grow. The deployment timeline diagram shows the realistic time expectations. 5 minutes for virtual WAN creation, 45 minutes for hubs, 30 minutes for gateways. In total, you're looking at about 90 to 95 minutes for a basic deployment. The deployment best practices listed are learned from real-world experience. Deploying hubs in parallel can cut deployment time in half. Using no wait for long operations lets you continue with other tasks. Proper error handling and logging help diagnose issues quickly. Tagging ensures resources do not get lost or misallocated. Validation at each step prevents cascading failures. And keeping scripts in source control enables infrastructure as code practices and team collaboration. VPN connectivity configuration. Configuring VPN connectivity in virtual WAN involves multiple layers of configuration, from defining sites to establishing tunnels to optimizing performance. Let me guide you through each aspect with real-world examples and hard-learned lessons from production deployments. Site configuration begins with understanding your on-premises infrastructure. Each VPN site in virtual WAN represents a physical location with one or more VPN devices. The AZ Network VPN site create command captures this information. The device vendor parameter is not just metadata. Virtual WAN uses it to generate device-specific configuration scripts. I've seen deployments fail because someone selected generic when they had a Cisco ASA, resulting in incompatible configurations. Always specify the exact vendor and model. The link configuration within each site is where you define your actual connectivity. Using AZ Network VPN Site Link Add, you can configure multiple links per site for redundancy. The provider name parameter helps track which ISP provides each link. This is invaluable during outage troubleshooting. The link speed parameter should reflect the actual bandwidth of your internet connection, not your desired VPN throughput. This helps virtual WAN make intelligent routing decisions when you have multiple links with different capacities. BGP configuration transforms your VPN from static to dynamic routing. The AZ Network VPN site update command with ASN and BGP peering address parameters enables BGP. The ASN, Autonomous System Number, must be unique within your virtual WAN. I maintain a registry of assigned ASNs to avoid conflicts. The BGP peering address must be from a non-overlapping range. I typically use linked local addresses, 169.254.x.x, to avoid conflicts with production networks. BGP isn't just about dynamic routing. It enables automatic failover and load balancing across multiple tunnels. Creating VPN connections brings everything together. The AZ Network VPN Gateway Connection Create command establishes the actual tunnels. The remote VPN site parameter links to your site definition. If you're using BGP, ensure Enable BGP is set to True. The connection automatically creates two tunnels for redundancy, each terminating on different gateway instances. This active-active configuration means you get automatic failover and load balancing without additional configuration. The device configuration scripts that virtual WAN generates are incredibly helpful but require understanding. Using AZ Network VPN Site Download Config, you get a JSON file with complete device configurations. For supported devices like Cisco ISR or ASA, you can often paste these configurations directly. However, always review them first. I've seen cases where firewall rules or NAT configurations on the device interfered with the generated config. The script includes both IKE, Phase 1, and IPsec, Phase 2, parameters, pre-shared keys, and even BGP configurations if enabled. Performance optimization for VPN connections involves several techniques. First, ensure your on-premises internet connection isn't the bottleneck. A 10 gigabits per second VPN gateway won't help if you have a 100 megabits per second internet circuit. Second, consider traffic patterns. If most traffic is internet-bound, enable local internet breakout to avoid hairpinning through Azure. Third, monitor and adjust MSS clamping values if you're seeing fragmentation. The default MSS of 1350 works for most scenarios, but some applications might benefit from tuning. Finally, if you need guaranteed performance, consider ExpressRoute instead of or alongside VPN. ExpressRoute integration. ExpressRoute integration with virtual WAN opens up possibilities for high bandwidth, low latency, and highly reliable connectivity. Unlike standalone ExpressRoute deployments, virtual WAN's integration provides automatic failover, simplified routing, and global reach. Let me walk you through the complete process of integrating ExpressRoute with your virtual WAN. First, let's understand what makes ExpressRoute in virtual WAN special. When you connect an ExpressRoute circuit to a virtual WAN hub, you are not just getting private connectivity to that hub. You are getting access to the entire virtual WAN fabric. A circuit connected in Chicago can reach resources in Tokyo, Sydney, or London through Microsoft's backbone. This global reach comes without additional configuration or complex routing setups. The ExpressRoute gateway creation process starts with a AZ-Network ExpressRoute Gateway Create. The scale units parameter determines your bandwidth capacity. Unlike VPN gateways where scale units are additive, each unit adds 500 megabits per second. ExpressRoute gateway scale units map to specific bandwidth tiers. For the standard gateway, 2 scale units provide 2 gigabits per second, while for the high-performance gateway, 2 scale units provide 10 gigabits per second. Choose based on your circuit bandwidth and expected growth. Creating the connection between your ExpressRoute circuit and the virtual WAN hub requires specific permissions. The AZ-Network ExpressRoute Gateway Connection Create command needs the circuit's resource ID, which includes the service key. Many organizations struggle here because the circuit might be in a different subscription or even a different Azure Active Directory tenant. The authorization key parameter handles cross-subscription scenarios. The circuit owner generates this key using AZ-Network ExpressRoute Auth Create. The routing configuration for ExpressRoute in virtual WAN deserves special attention. By default, ExpressRoute connections learn all routes from the virtual WAN and advertise all on-premises routes. This might not always be desirable. Using the routing configuration parameter, you can control route propagation. For example, you might want your ExpressRoute connection to only learn production VNet routes, not development ones. This granular control prevents accidental exposure of environments. Global reach configuration enables direct connectivity between ExpressRoute circuits through virtual WAN. If you have circuits in multiple regions, enabling global reach allows your on-premises locations to communicate directly through Microsoft's backbone without traversing your virtual WAN hubs. The AZ-Network ExpressRoute Peering Connection Create command establishes these connections. I typically recommend global reach for scenarios where you have high bandwidth requirements between on-premises locations. Performance considerations for ExpressRoute in virtual WAN go beyond just bandwidth. Latency is deterministic and typically excellent. Expect 1 to 2 milliseconds between your premises and the Microsoft Edge. However, remember that virtual WAN adds processing time, typically 2 to 5 milliseconds through the hub. For ultra-low latency applications, you might need ExpressRoute FastPath, which bypasses the gateway for specific flows. Also consider circuit redundancy. I always recommend paired circuits terminating in different peering locations for true high availability. Virtual network connections. Connecting virtual networks to virtual WAN is where many of the platform's benefits become apparent. Unlike traditional VNet peering with its transitive routing limitations, virtual WAN connections provide full any-to-any connectivity with intelligent routing. Let me guide you through the nuances of VNet connectivity that will help you build efficient, scalable networks. The fundamental difference between virtual WAN VNet connections and traditional peering lies in the routing behavior. When you connect a VNet to virtual WAN using AZ-Network vHub Connection Create, that VNet immediately gains access to all routes known to the virtual WAN. This includes routes to other VNets, branches, ExpressRoute circuits, and even internet destinations if configured. The magic happens through Azure's software-defined networking, which programs the effective routes directly into the VNet's routing tables. Understanding the connection parameters is crucial for proper configuration. The remote VNet parameter accepts the full resource ID of the target VNet. The name parameter should follow a naming convention that identifies both the hub and VNet for easier management. I use patterns like ConHub East US VNet Prod app. The associated route table parameter is where you define which route table this VNet uses for routing decisions. Most deployments use the default route table, but custom route tables enable advanced segmentation scenarios. Route propagation configuration determines how this VNet's address space is advertised throughout your virtual WAN. The propagated route tables parameter accepts a list of route table IDs. By default, VNet routes propagate to the default route table, making them reachable from everywhere. However, you might want to limit propagation for secure environments. For example, a VNet containing sensitive databases might only propagate to a secure route table associated with authorized connections. The static routes parameter enables route injection for scenarios where dynamic routing isn't sufficient. Common use cases include advertising a subset of a VNet's address space, useful during migrations, routing specific prefixes through network virtual appliances, or creating null routes for security purposes. Each static route requires a name, address prefix, and next hop IP. Remember that static routes have higher precedence than dynamically learned routes. Performance optimization for VNet connections starts with understanding traffic patterns. Virtual WAN uses the Microsoft backbone for inter-VNet traffic, providing consistent low latency. However, the hub adds processing overhead. For VNets in the same region requiring ultra-low latency, you might consider direct VNet peering alongside virtual WAN connections. This hybrid approach gives you the best of both worlds: direct paths for high-performance workloads and virtual WAN routing for everything else. Troubleshooting VNet connectivity issues requires a systematic approach. First, verify the connection state using AZ-Network V-Hub connection show. The provisioning state should be succeeded. Next, check effective routes in the VNet using AZ-Network NIC show effective route table. You should see routes with next hop type virtual network gateway for destinations reachable through virtual WAN. If routes are missing, verify route table associations and propagation settings. Remember that network security groups and Azure firewall rules might also block traffic even when routing is correct. Routing architecture and design. Routing is the heart of virtual WAN, and understanding its architecture is essential for building efficient, scalable networks. Virtual WAN's routing is fundamentally different from traditional networking. It's intent-based rather than configuration-based. Let me take you through the routing architecture, from basic concepts to advanced designs. The routing architecture in virtual WAN is built on three pillars: route tables, route associations, and route propagations. Route tables are containers for routes, similar to traditional routing tables but with added intelligence. Each hub has a default route table created automatically, and you can create custom route tables for advanced scenarios. Routes in these tables come from multiple sources. Connected VNets advertise their address spaces. VPN sites advertise on-premises prefixes through BGP or static configuration, and express route circuits bring in routes from your private network. Route association determines which route table a connection uses for making forwarding decisions. When traffic arrives at a connection, VNet, VPN, or express route, virtual WAN consults the associated route table to determine the next hop. The AZ-Network V-Hub connection update command's associated route table parameter controls this association. Think of it as selecting which routing brain a connection should use. Most connections use the default route table, but associating with custom route tables enables traffic segmentation. Route propagation controls which route tables learn about a connection's routes. This is where virtual WAN's power becomes apparent. A single VNet can propagate its routes to multiple route tables simultaneously using the propagated route tables parameter. This enables scenarios like shared services. A VNet containing common resources can propagate to all route tables, making it reachable from everywhere, while isolated VNets only propagate to specific tables. The route evaluation process follows a specific order of precedence. Static routes have the highest priority, followed by BGP-learned routes, then system routes. Within each category, more specific routes, longer prefix matches, take precedence. Understanding this hierarchy is crucial when designing complex routing scenarios. For example, If you have a default route, quad 0/0, learned via BGP in a specific route, 10.1.0.0/16, configured statically, traffic to 10.1.0.0/16 will follow the static route. Custom route tables enable advanced network segmentation. I recently designed a network with 4 custom route tables: production, development, shared services, and DMZ. Production VNets only propagated to the production and shared services tables. Development VNets only propagated to development and shared services. This design ensured complete isolation between production and development while both could access shared services. The DMZ table had specific routes to internet-facing services but no routes to internal networks. Inter-hub routing adds another layer of sophistication. When you have multiple hubs, virtual WAN automatically programs routes between them. The non-propagation label prevents routes from propagating between hubs. This is useful for region-specific resources. The default label ensures global propagation. You can create custom labels for fine-grained control. For example, a US-only label might limit propagation to hubs in US regions for compliance reasons. Building on our routing foundation, let us explore advanced routing scenarios that solve complex real-world requirements. These patterns go beyond basic connectivity to address security, compliance, performance, and operational needs. I will share configurations I have implemented in production environments serving millions of users. The first advanced scenario is forced tunneling, where all internet-bound traffic must route through on-premises security appliances. This common requirement in regulated industries requires careful configuration. Using AZ Network vHub Route Table Route Add, you create a default route, quad 0/0, pointing to your on-premises network via VPN or express route. The next hop type is IP address with your on-premises firewall as the target. Remember to exclude Azure service traffic using service tags, or you will break platform functionality. Implementing a security inspection architecture requires routing all interspoke traffic through Azure Firewall or a third-party NVA. The secured virtual hub pattern handles this automatically, but you can achieve similar results with custom routing. Create static routes for each spoke's address space pointing to the firewall's IP. The key insight is that you need routes in both directions, spoke A to firewall and firewall to spoke B. This bidirectional routing ensures symmetric traffic flow, which is crucial for stateful inspection. Multi-region failover routing showcases virtual WAN's intelligence. In a recent deployment, we had primary resources in East US with disaster recovery in West US during normal operations, all traffic routed to East US. We implemented BGPAS path prepending on the West US connections, making those routes less preferred. During failover, we removed the prepending, causing automatic reconvergence to West US. The beauty is that this works globally. Branches in Europe automatically failed over without any local configuration changes. The hub-to-hub routing optimization scenario addresses performance requirements between specific regions. While virtual WAN automatically meshes hubs, you might want to influence path selection. Using BGP communities, you can mark routes from specific hubs and create routing policies based on these markings. For example, routes from Asian hubs might prefer paths through Middle East hubs rather than European hubs for geographic proximity. Selective route advertisement enables granular control over what each site or VNet can reach. Instead of the default any-to-any connectivity, you might want Site A to only reach specific VNets. Create a custom route table that only has routes to authorized destinations. Associate Site A's connection with this table. This approach is more maintainable than using firewall rules because it prevents traffic from even attempting unauthorized paths. The route summarization scenario becomes critical in large deployments. If you have hundreds of sites each advertising multiple prefixes, route table sizes can become unwieldy. Implement summarization at strategic points, typically at regional boundaries. For example, All US sites might be in 10.1.0.0/16, European sites in 10.2.0.0/16, and so on. Configure BGP on regional hub connections to advertise summary routes instead of specific prefixes. This reduces route table entries from thousands to dozens, improving convergence times and reducing memory usage. Security integration with virtual WAN. Security in virtual WAN is comprehensive and multi-layered, as shown on this slide. Let's start with the Azure Firewall deployment command at the top. Notice we are creating a firewall with the vHub parameter, which deploys it directly into the virtual WAN hub. The SKU AZ-700 hub is specifically optimized for virtual WAN, and the premium tier enables advanced features like TLS inspection and intrusion detection. The public IP count 2 provides redundancy for outbound connections. The firewall policy creation shows how to implement hierarchical security policies. The Threat Intel Mode Alert enables Microsoft's threat intelligence feeds. DNS proxy enabled allows the firewall to act as a DNS proxy for better security visibility, and Intrusion Detection Mode Alert provides signature-based threat detection. These are not just checkboxes, they fundamentally enhance your security posture. Looking at the rule collection group creation, you can see how granular control is implemented. The priority system, 100 in this example, determines rule evaluation order. The application rule shown allows HTTPS traffic to Microsoft and Azure domains, but notice it also includes web categories like computers and technology. This categorical filtering is powerful for controlling access without maintaining massive URL lists. The security architecture layers diagram illustrates defense in depth. At the perimeter, you have DDoS protection and web application firewall. The network layer includes Azure Firewall, NSGs, and application security groups. Identity security leverages Azure AD with conditional access and MFA. Finally, data security uses private endpoints, TLS encryption, and key vault. Each layer protects against different threat vectors. The Security Integration Components table breaks down where each component operates. Azure Firewall works at Layer 4 to Layer 7 per hub with features like TLS inspection and IDPS. DDoS protection operates at the VNet level with automatic mitigation. NSGs provide microsegmentation at subnet or NIC level using stateful rules. Private Endpoints secure platform as a service with private IP access and DNS integration. The Zero Trust implementation principles shown are crucial. Never trust, always verify means all traffic is inspected regardless of source. Least privilege access is implemented through granular routing and firewall rules. Assume breach mentality drives multiple security layers and comprehensive monitoring. Verify explicitly requires strong authentication and conditional access. This is not just theory, it is how modern secure networks are built. Point-to-site VPN configuration. The point-to-site VPN configuration shown on this slide represents enterprise-scale remote access. The first command creates a P2S gateway with 10 scale units, supporting up to 5,000 concurrent users. Each unit supports 500 users. The address prefixes 172.16.0.0/20 and 172.16.16.0/20 provide 8,192 addresses, allowing for growth and multiple address pools for different user groups. The Azure AD authentication configuration is particularly important. The AAD tenant parameter points to your Azure AD tenant. Odd audience uses the Azure VPN application ID, and odd issuer identifies the token issuer. This integration enables modern authentication with conditional access policies, eliminating the need for certificate management. The split tunneling configuration using custom routes is crucial for performance and user experience. By specifying RFC 1918, only corporate traffic goes through the VPN tunnel. Internet traffic goes directly from the user's location, reducing latency and VPN gateway load. The associated route table parameter ensures P2S users inherit the correct routing policies. The diagram shows the complete flow from remote users through authentication to resource access. Users on Windows, Mac, and mobile devices connect to Azure AD for authentication. Conditional access policies can enforce requirements like device compliance or location restrictions. After successful authentication and any required MFA challenges, users connect to the P2S gateway, which provides access to the virtual hub and its routing infrastructure. The P2S configuration options table outlines key decisions. Azure AD authentication enables conditional access for enterprise scenarios. OpenVPN protocol provides cross-platform support essential for BYOD split tunneling with custom routes optimizes performance for hybrid workers. The scale units from 1 to 20 support 500 to 10,000 users with elastic scaling for global workforces. This configuration transforms remote access from a point solution to an integrated part of your global network. Users anywhere in the world can connect to their nearest P2S gateway and access resources globally through Virtual WAN's routing fabric, all while maintaining security through Azure AD integration and conditional access policy. Multi-region high availability. This slide illustrates architecting for true global high availability. The diagram shows a primary region, East US, with active VPN and ExpressRoute gateways connected to production VNets, and a secondary region, West US, with standby VPN gateway but active ExpressRoute gateway connected to DRV nets. Notice how branches have connections to both regions. Solid lines to the primary and dotted lines to the secondary, indicating the failover paths. The configuration commands demonstrate how to implement this architecture. The primary hub connection has a routing weight of 100, making it preferred, while the secondary has a weight of 50. This ensures traffic flows through the primary under normal conditions. Both connections have enabled BGP True for dynamic routing and automatic failover. The BGP configuration with redundancy mode active ensures both paths are maintained and monitored continuously. ExpressRoute geographic redundancy shown uses premium SKU circuits in different peering locations, Washington, D.C. in this example. This provides path diversity at the physical layer, crucial for true high availability. The SKU tier premium is required for global routing and accessing resources across regions. The high availability design patterns comparison shows two approaches. Active-passive has the primary region handling all traffic with secondary on standby, resulting in lower cost but RPO of 15 to 30 minutes and RTO of 5 to 10 minutes. Active has both regions handling traffic with load balancing, higher cost, but RPO under 1 minute and instant RTO. Choose based on your business requirements and budget. The component failover times table is critical for setting expectations. Virtual hubs are always active with instant failover. VPN connections fail over in under 30 seconds as BGP detects the failure and reconverges. ExpressRoute fails over in under 5 seconds due to BFD, bidirectional forwarding detection. VNet connections take 2 to 5 minutes as they need to be recreated in the secondary region. This architecture provides resilience against multiple failure scenarios. Individual component failures are handled automatically. Regional failures trigger rapid failover to the secondary region. And even global service issues can be mitigated by having diverse connectivity paths. The investment in redundancy pays off when you need it most. Monitoring and diagnostics deep dive. Comprehensive monitoring and diagnostics are essential for managing virtual WAN at scale. The diagnostic settings command shown enables all critical log categories with appropriate retention periods. Route tables and gateway logs get 90-day retention for operational troubleshooting, while IKE diagnostic logs get 365-day retention for security and compliance. The metrics are retained for 30 days with full granularity. The metric alert configuration demonstrates proactive monitoring. Setting alerts for CPU usage above 85% with a 5-minute window and 1-minute evaluation frequency provides early warning before performance impacts occur. The Severity 1 classification ensures immediate notification to your action group. Similar alerts should be configured for bandwidth utilization, tunnel counts, and BGP session status. Connection monitor setup for end-to-end testing is crucial. The configuration shown tests from a branch route simulator to an Azure application over HTTPS, port 443. The threshold failed %5 and threshold round-trip time 100 define acceptable performance parameters. This synthetic monitoring catches issues before users report them. The monitoring architecture diagram shows the complete observability stack. Metrics, logs, traces, and flow logs feed into log analytics, which serves as the central repository. Application Insights provides application-level telemetry, while Sentinel adds security intelligence. This data drives dashboards, workbooks, and Power BI reports for visualization, and triggers alerts that invoke runbooks and logic apps for automated remediation. The Key Monitoring Metrics table provides actionable thresholds. Gateway health metrics, CPU and memory, above 80% indicate need for scaling. Connectivity metrics below expected values require investigation. Performance baselines plus 50% suggest optimization opportunities. Route counts above 10,000 require summarization to prevent routing table exhaustion. The troubleshooting toolkit listed combines native Azure tools for comprehensive diagnostics. Network Watcher provides packet capture and flow verification. Connection Monitor enables continuous testing. Traffic Analytics reveals patterns and anomalies. Azure Monitor centralizes metrics and logs. Resource Health indicates service-level issues. Together, these tools provide visibility into every aspect of your virtual WAN deployment. Cost optimization in virtual WAN can deliver 40 to 60% savings without compromising functionality. The metric cards show the potential. 40 to 60% savings through optimization, 30% typical waste from over-provisioning, and a 3 to 6 month ROI timeline. These are not theoretical. They are based on real customer implementations. The utilization analysis command queries actual bandwidth usage over a month, returning hourly averages. This data drives right-sizing decisions. The auto-scaling configuration shown implements dynamic scaling between 2 and 10 scale units. The scale-out rule adds 2 units when bandwidth exceeds 1500 megabits per second for 15 minutes, while the scale-in rule removes 1 unit when below 500 megabits per second for 30 minutes. The asymmetric timing prevents flapping. The cost breakdown analysis table reveals where money goes and where to save. Virtual hubs at $9.1250 per month for 5 hubs can be reduced to 3 hubs by consolidating low-traffic regions, saving $365 per month. VPN gateways with 20 units costing $5,270.60 can be right-sized to 12 units, saving $2,108.24. ExpressRoute gateway downsizing from 10 gigabits per second to 2 gigabits per second saves $2,920. Local breakout for internet traffic cuts data processing costs in half. Total potential savings: 54% or $6,268.24 monthly. The cost optimization strategies go beyond simple right-sizing. Gateway monitoring ensures you are not paying for unused capacity. Hub consolidation requires balancing latency requirements with cost. Local breakout for internet traffic is often the quickest win. Why pay to backhaul YouTube traffic through Azure? Reserved instances for connected virtual machines provide predictable discounts. Automated scaling prevents both over-provisioning and under-provisioning. Regular monthly reviews catch configuration drift and orphaned resources. The key is treating cost optimization as an ongoing process, not a one-time exercise. Set up automated reports showing virtual WAN costs by component, region, and cost center. Review utilization metrics monthly and adjust scale units accordingly. Implement show back or charge back to make teams aware of their network costs. Use tags extensively to track resource ownership and purpose. Remember that the goal is not minimum cost, but maximum value. Sometimes paying for extra capacity provides business value through improved performance or redundancy. The optimization strategies shown help you make informed decisions about where to invest and where to save, ultimately delivering a network that meets business needs at optimal cost. Migration strategies. Migrating to virtual WAN requires careful planning and execution. The migration flow diagram shows the 4 phases: assessment, parallel build, migration, and optimization. Each phase builds on the previous one, with specific activities flowing from documenting current state through to final cost optimization. The migration script demonstrates a practical approach to migrating VNets. It starts by documenting the current peering configuration. This backup is crucial if rollback is needed. The script then creates the virtual WAN connection in parallel with existing connectivity, avoiding downtime. After a 5-minute wait for provisioning, routes are updated to prefer virtual WAN paths. Only after confirming traffic flow through virtual WAN is the old peering removed during a maintenance window. The migration patterns comparison shows 2 approaches. Big Bang migration converts everything during a single maintenance window. It is faster overall with a shorter project timeline but carries higher risk and requires extensive testing. This approach works well for smaller networks where you can control all variables. Phased migration transitions gradually with lower risk per change but takes longer. The learning opportunities during phased migration help refine the process for subsequent waves. Large enterprises almost always choose phased migration. The timeline table provides realistic expectations. Assessment takes 2 to 4 weeks to document everything and create a complete inventory. The pilot phase runs 2 to 3 weeks with test sites to verify connectivity. Production migration spans 4 to 12 weeks depending on network size, with success measured by all sites being migrated. Optimization takes another 2 to 4 weeks to clean up legacy resources and tune performance, with success measured by meeting cost targets. The key to successful migration is treating it as a journey, not a destination. Start with non-critical workloads to build confidence. Document everything. What worked, what did not, and why. Use the pilot phase to refine your runbooks and scripts. Most importantly, communicate extensively with stakeholders. Network migrations affect everyone, and setting proper expectations prevents frustration. Remember that virtual WAN is fundamentally different from traditional hub and spoke networks. Do not try to recreate your existing architecture in virtual WAN. Embrace the new paradigm of intent-based networking and let virtual WAN handle the complexity for you. Automation and infrastructure as code. The Terraform module shown demonstrates infrastructure as code best practices for virtual WAN. Notice how the module creates the virtual WAN resource with all necessary parameters, then uses A for each loop to create multiple hubs based on the hub locations variable. This approach makes it trivial to add new regions. Just update the variable. The module also creates VPN gateways for each hub, with scale units configurable per region. The Azure DevOps pipeline automates deployment with proper controls. The trigger configuration runs the pipeline when changes are made to virtual WAN Terraform files. The plan stage validates changes without applying them, while the deploy stage only runs on the main branch and requires environment approval. This prevents accidental production changes while enabling rapid iteration in development. The automation architecture diagram shows how different components work together. Source control, Git, contains Terraform modules and PowerShell scripts. CI/CD platforms like Azure DevOps or GitHub Actions orchestrate deployments. Execution happens through Azure Automation, Functions, and Logic apps. Everything feeds into monitoring through Azure Monitor and Application Insights. This creates a closed-loop system where deployments are automated, monitored, and continuously improved. The automation use cases table demonstrates real efficiency gains. Site provisioning that manually takes 2 hours can be automated to 5 minutes using PowerShell and DevOps. Gateway scaling with Azure Functions provides real-time response to load changes, optimizing costs automatically. Compliance checks through Azure Policy run continuously, ensuring 100% compliance without manual reviews. Daily backup configurations through Logic apps provide disaster recovery capabilities without human intervention. The key to successful automation is starting small and building incrementally. Begin by automating repetitive tasks like adding branch sites. Build libraries of reusable modules for common patterns. Implement proper testing. Automated deployments can break things faster than manual ones. Use version control for everything, including scripts and configurations. Troubleshooting complex issues. The KQL queries shown are powerful tools for investigating virtual WAN issues. The first query finds all routing changes in the last 24 hours, parsing the JSON properties to show what routes were added or removed. This is invaluable when connectivity suddenly breaks. You can quickly identify what changed. The second query correlates tunnel failures with BGP events, looking for events within 5 minutes of each other. This correlation often reveals root causes that would be difficult to spot manually. The PowerShell troubleshooting function provides a systematic approach to connectivity testing. It starts by checking virtual WAN and hub health, then examines each gateway's status and scale units. The route count check is important. Excessive routes can cause performance issues. Finally, it performs actual connectivity tests using Network Watcher, providing hop-by-hop analysis if the test fails. The troubleshooting flow diagram illustrates the decision tree for issue resolution. Starting with service health eliminates Azure-wide issues. Component health checks identify failed gateways or hubs. Routing analysis catches misconfigured route tables. Security rule validation finds blocking NSGs or firewall rules. Performance analysis identifies capacity issues. This systematic approach prevents jumping to conclusions and missing the real problem. The common issues and solutions table comes from real-world experience. Intermittent connectivity often stems from BGP flapping. Stabilizing BGP timers by increasing hold times usually resolves this. Poor performance with high latency frequently indicates suboptimal routing. Adjusting route weights to prefer better paths fixes it. Connection failures that can't establish are often IKE parameter mismatches. Verifying both sides use compatible settings solves this. Missing routes where resources are unreachable typically involve propagation settings. Checking route table labels and associations reveals the issue. Advanced troubleshooting requires thinking beyond individual components. Use distributed tracing to follow traffic flows across multiple hops. Correlate events across different data sources. A storage timeout might manifest as a VPN performance issue. Consider timing. Many issues only occur during peak hours or maintenance windows. Document your findings thoroughly. The weird issue you solve today will recur in 6 months. The most important troubleshooting skill is knowing when to escalate. Virtual WAN is a managed service, and some issues require Microsoft support. Collect comprehensive diagnostics before opening a case. Support engineers need logs, metrics, and specific error messages to help effectively. Future-proofing your virtual WAN. The technology evolution diagram shows the roadmap for virtual WAN and enterprise networking. In the near term, 6 to 12 months, we are seeing IPv6 support rolling out, SASE integration becoming standard, and AI-driven operations emerging. The medium term, 1 to 2 years, brings quantum-safe cryptography as organizations prepare for post-quantum threats, edge computing integration for IoT scenarios, and 5G network integration. Long term, 3+ years, expect full automation with self-healing networks, ML-based optimization that continuously improves routing, and native zero-trust architectures. The future-proofing checklist divides into architecture and operational readiness. Architecture readiness includes modular design patterns that can accommodate new features, API-first approaches enabling integration with future tools, multi-cloud readiness for hybrid scenarios, scalable IP addressing that will not require redesign, extensible security models that can add new controls, and automation foundations that can incorporate new capabilities. Operational readiness covers DevOps culture enabling rapid adoption, continuous learning keeping skills current, metric-driven decisions based on data, innovation pipelines for testing new features, vendor relationships for early access, and skills development programs. The code example shows future-ready patterns. Feature flags allow enabling preview features when they become available without code changes. The abstraction layer pattern shown with the network connectivity module provides provider-agnostic configuration. This means you could switch from virtual WAN to AWS Transit Gateway or Google Cloud Interconnect by changing a variable, not rewriting everything. The investment areas table maps current state to future state with specific actions. Architecture evolution from cloud-native to multi-cloud requires abstracting provider-specific implementations. Security transformation from perimeter-based to zero trust needs SASE implementation. Operations shift from reactive to predictive requires AI ops deployment. Skills evolution from network-focused to full-stack demands comprehensive training programs. The key strategies for future success emphasize adaptability. Design for change means assuming everything will evolve. Do not create rigid architectures. Automate everything because manual processes will not scale to future complexity. Best practices and conclusion. As we conclude this comprehensive journey through Azure Virtual WAN, let's consolidate the key insights and best practices. The metric cards show the transformative impact. 75% faster deployment times, 60% reduction in operational effort, and 99.99% typical availability. These aren't aspirational goals. They're what organizations achieve when virtual WAN is properly implemented. The top 10 best practices are distilled from hundreds of deployments. Starting with standard SKU avoids painful migrations later. Careful IP planning prevents address conflicts that are difficult to resolve. Designing for failure with N+1 redundancy ensures business continuity. Documenting everything creates institutional knowledge. Automating from day one builds operational efficiency. Proactive monitoring catches issues before users complain. Defense in-depth security protects against evolving threats. Regular cost reviews prevent bill shock. Disaster recovery testing ensures your plans actually work. And investing in training empowers your team to maximize virtual WAN's capabilities. The virtual WAN maturity model shows the evolution path. Level 1 basic connectivity gets you started with simple hub and spoke and manual operations. Level 2 advanced networking adds multi-region deployment and basic automation. Level 3 optimized operations brings full automation and cost optimization. Level 4 business transformation introduces self-service portals and business metrics focus. Level 5 innovation platform achieves multi-cloud integration and zero-touch operations. Most organizations take 18 to 24 months to progress from level 1 to level 4. The key success metrics table quantifies the transformation. New site deployment time drops from weeks to hours, a 98% improvement. Network changes that took 5 days now complete in 30 minutes, 99% faster. Incident resolution improves from 4 hours to 15 minutes, 94% reduction. Operating costs typically drop 60% from $50K to $20K monthly. These metrics justify the investment and effort required for virtual WAN adoption. Your next steps form a continuous improvement cycle. Complete your learning with hands-on labs and additional training. Design your architecture based on business requirements, not technical constraints. Build a proof of concept to validate your design. Plan migration carefully with stakeholder buy-in. Deploy to production with proper change management. Then optimize continuously. Virtual WAN keeps improving, and so should your implementation. Remember, virtual WAN is not just a technology upgrade, it's a transformation enabler. It fundamentally changes how you think about networking, from managing individual components to defining intent and policy. Embrace this paradigm shift, and you'll build networks that are not just technically superior but genuinely enable business agility and innovation. Thank you for joining this comprehensive exploration of Azure Virtual WAN. Now go build something amazing. Thank you for your attendance. Please consider subscribing to the channel.